So in this video, we're going to learn how to compute the DFT efficiently. And what this has to do with is how much time does it take to compute a spectrum, and how does that time depend on the amount of data, the length of the transform. If you're like me, you want that spectral calculation to come back as soon as possible, the computation to be quick. That's where efficiency comes in. We want to find out how to compute the DFT as quickly as possible. And it turns out this has led to the discovery of something called the fast Fourier transform, just a way of computing the DFT. It's not a new transform, it's just a way of computing the DFT. And it's known as the FFT in the digital signal processing world. To talk about this, we're going to introduce the concept of computational complexity that comes from computer science, that has a systematic way of evaluating how many computations and how a program, a formula is going to require. So let's look at the DFT formula. So we have to compute this formula. This is the formula we've seen before. And I want to look at what do I have to do for each frequency. So K is fixed here. The complex exponential is fixed in terms of K. And now I want to do this multiplication by S of n times the complex exponential and add the results up. So how much work is required? So what work means, computations means, I'm going to consider multiplications and additions in some detail. So every term in this sum has this multiply in it. And recall that that's a complex exponential, which means it's a complex number. And in most computers, in fact all computers I know of, complex numbers are stored as real and imaginary parts, very convenient for doing the multiplication. So this formula becomes that, and that means I have two multiplications in here that are real multiplications, and that's what we want to consider. No computer I know of has inherently built-in complex arithmetic properties, so we're going to talk about this in terms of real multiplications. So we have two real multiplications for every term in the sum, and we have n terms in the sum, so we get 2n for the number of real multiplies. How about additions? So in terms of additions, point out something rather straightforward. Suppose you're adding up three numbers. You only need to do two additions. So the number of additions in the sum with n terms is n minus 1. And because we have to sum the real and imaginary parts separately, that's where the factor of 2 comes in. One for the real part, one for the imaginary. So total number of computations that's going to be required is 4n minus 2, just adding up those two numbers. So, but this is there for each frequency. Since we have to evaluate this for n different frequencies, we come up with a total number of computations that's n times 4n minus 2 computations. So writing this out a little bit here, this is 4n squared minus 2n. Okay, so to summarize this in a way that's a bit more manageable, the concept of computational complexity has arose. And computational complexity is worried about the worst case behavior. What happens as n goes to infinity, as n gets big? The term that dominates clearly is the quadratic term. You can essentially forget about this when n gets big. You want to see that, take n, it'd be 1,000. This is well over 1,000,000, and you subtract off a couple of thousand. It doesn't matter very much. Furthermore, we don't worry about the constant in front in computational complexity because we're worried about how fast things compute. This is going to depend on the speed of the computer, and the factor 4 really doesn't tell us very much about that. What we want to know is, in essence, on the same computer, how much more work is going to be required as I change the number of points in the transform, the term capital N. So what is known as the computational complexity of this calculation is n squared. And this is read as this is an order n squared computation. Again, all you do is look at the number of computations and look at the worst case term, drop any constants that may be in front, and that tells you that as this, if you double the length of the transform, it's going to take you 4 times longer. That's the kind of information that you want. Well, not being satisfied with that result, some guy named Gauss, yes, that Gauss, in 1805, figured out a more efficient, what that means is a smaller computational complexity than this formula would first appear. He can compute the DFT rather efficiently, and it's now known as the fast Fourier transform, or the FFT. Turns out he discovered this in 1805. He never published it in his lifetime. He wrote it in his personal notes, put it in a drawer. It was only discovered after he died, and his collected works, including what was in the drawer, were published. If you want to read more about this, I wrote a paper about the history of the FFT and Gauss, which you may find interesting. But let's see if we can learn what Gauss's thinking was. He made an assumption, which is not a very bad one. He assumed that the transform length was 2 to a power. This is one of the reasons why those powers of 2 I showed you in a previous video are very important to learn. They have to do with transform lengths in the FFT. Now, we know from our discussion of the DFT that all that we have to have is that the transform length be greater than or equal to the actual signal duration. So what I'm doing is changing the signal duration. I'm assuming that the transform length is 2 to a power, and so what's normally done in practice is that whatever your length of data is, 608, I pick up the next power 2 that's just bigger than that, and the DFT will work and won't be any problem. I'm going to have to pad with zeros. Okay, so that's okay. So let's see what Gauss did. What Gauss did was he separated this sum into a sum of the even numbered terms and a sum of the odd numbered terms. So he hasn't changed any kind of computational complexity at all, but he's a mathematician. He's going to play with the formulas a little bit. You then noticed he could write them a bit more succinctly in the following way, and so he pulls out a phase factor out of the expression for the odd numbered terms. And then he noticed that these exponentials for corresponding terms in the 2 are all the same. So we have the same computation going up here as we do down here, and we take the one for the odd numbered terms, multiply by this, add them up, and that gives us the DFT. Again, this hasn't saved any work yet. In fact, it may look like we're going to have to do more work because we're going to have to multiply by this thing to use this result. Gauss has a little surprise for us. So let's look at this expression again. So here's our formula for the DFT, and I want to point out what's critical here is we have to evaluate this right at our n frequency values. So I have to evaluate this thing at capital N values, this thing at capital N values, multiply by this, and add them all up. Well, what he noticed, first of all, was that each of these is an n over 2 length DFT. You can see I am sampling here by k divided by n over 2. So these are DFT formulas. Well, that's kind of interesting, I guess. So this is a DFT of the even numbered terms. This is a DFT of the odd numbered terms. I multiply the one for the odd numbered terms by a complex exponential, add them up, and I get what I want. Again, I still haven't saved anything yet until Gauss, being a very smart mathematician, realized one of the properties of the DFT. The DFT is periodic in its length. This thing is periodic with a period of n over 2. So, what does that mean? That means that once I calculate this formula for 0 up to n over 2 minus 1, what happens at n over 2 is the same thing that happens at 0. And what happens at n over 2 plus 1 is the same thing that happened at 1. I don't need to compute these formulas for the higher values of k. I can reuse my previous computations. The only ones I need to compute are the ones here for the first half. After that, to evaluate these two DFTs, I just reuse my values. It's periodic because of the properties of the DFT. I do have to multiply by this for every value of k. There are no special properties of that. But still, I've saved half my computations. Say that again. I've saved half right away. So let's see, in terms of a block diagram, what Gauss's insight was. He says, I can take the original sequence, original data, and I can divide it into the even numbered terms and the odd numbered terms. I can take the length 4 DFT of each. So this is this expression, and that is this expression. And to compute the spectrum at value 0, I take the value for k equals 0 from that DFT, the value for k equals 0 for that DFT, multiplying by the complex exponential, which is pretty easy, and add them up. And I do the same thing, similar thing for S1, S2, S3, but when it comes down to S4, I can reuse the values I've already computed for the DFT. I have to multiply the odd number DFT by a different complex exponential, but that's what I do. All right. So, and this saves half the work. It's pretty clear. I do not have to evaluate these length 4 DFTs for 8 different values. I only do it for 4 each. Well, this is a power of 2. What Gauss then knows is that n, since n is a power of 2, n over 2 is also a power of 2. I can do it again and keep doing it until I get down to length 2 transforms. So in our length 8 example, here's what he, first stage of his decomposition, he then decomposes each of these into length 2 DFTs. And he decomposes the length 4 DFT, the evens, into 2 length 2 DFTs. Now he saved another factor of 2 in computations. So this keeps going. If you have a higher power of 2, you can keep doing it and doing it and doing it. Get increasing your computational savings. So now let's look at the details and see what we've got. So the FFT divides everything into stages, and the number of stages is equal to the number of times we had to divide by 2. So since n we assumed was 2 to a power, the number of stages is the log 2 of n, which of course is equal to L. So we have L stages, each of which consist of n over 2, length 2 DFTs. If you look at every stage in this diagram, you'll see that that's true. All right, now every pair of length 2 DFTs is combined after one is multiplied by a complex exponential. These These are combined together. And if you count up the number of computations, the real multiplies and adds, you get 10 computations each. So for each stage, you get 5 times n over 2. And the reason it's 5 is because there's 10 applied for every pair. So we get 5 n over 2 computations for every stage. The number of stages we got was log 2 of n. So the total complexity is going to be obtained by multiplying those together, and sure enough, we obtained the rather interesting result that the complexity of computing the FFT is n log n. So the question is this really a savings? I mean, this looks to be a bit more complicated program you'd have to write than the straightforward DFT. So let's compare their complexities. So on this plot, I have the DFT complexity, which is n squared, and I've compared that with that of the FFT, log 2 of n, n log 2 of n, however, only for the powers of 2. And I think you can see that there is a huge gap. Look at the far apart they are, and I want you to look at the vertical scale. That's in millions of operations. It is spectacularly more efficient to use the FFT than just to use the DFT in its raw form. Turns out it's been shown that there is no other algorithm for computing the spectrum that has a smaller complexity than the FFT. The FFT, in some sense, is the most efficient algorithm you can have. It has the smallest possible complexity. There is no other algorithm yet to be discovered that has a smaller complexity. So this is why the FFT is used pervasively. In fact, if you want to compute the DFT using Octave and MATLAB, the function name is FFT. So I want to point out that the FFT is spectacularly efficient for computing the DFT, much more so than just programming the formula for the DFT. But do want to emphasize this is not a new Fourier transform. Instead, it's an algorithm, a way of computing the DFT. It does nothing different than compute the DFT, but very efficiently, which means very quickly. So it has no more properties in terms of linearity and the properties, signal properties that we associate with the DFT. It's just a way of computing it. So there's nothing new in that regard. But it's so efficient that it really opens the door to many signal processing ideas, including computing a filter, the input-output of a filter in the frequency domain. It turns out that is really the way to go in many applications, and we're going to talk about that in the next video.